Machine learning is a powerful tool. It helps computers learn from data, and this lets them make predictions or decisions. Algorithms are the heart of machine learning. They are sets of rules that guide the learning process. Imagine you want to teach a computer to identify cats in pictures. You can use a machine learning algorithm. You would give it many pictures of cats and other animals. The algorithm would learn from the patterns in the images. Then, it could recognize cats in new pictures. There are many types of machine learning algorithms. Each has strengths and weaknesses. Choosing the right algorithm depends on the task, and it also depends on the type of data you have. Some popular algorithms include linear regression, support vector machines, and decision trees. In this essay, we will focus on decision trees. We will explain how they work and why they are useful. We will also discuss their limitations. A decision tree is a type of machine learning algorithm. It is used for both classification and regression tasks. In simple terms, a decision tree is like a flowchart. It asks a series of questions about the data. Based on the answers, it follows a path down the tree. Each path leads to a prediction or decision. Imagine you want to decide whether to wear a jacket outside. You might use a decision tree to help you decide. The tree might ask questions like, what is the temperature? Is it raining? Is it windy? Based on your answers, the decision tree would lead you to a decision. For example, if the temperature is below freezing, it is raining, and it is windy, the tree might recommend wearing a jacket. Decision trees are popular because they are easy to understand. They can be visualized as a tree structure. This makes it easy to see how the algorithm is making decisions. To understand how decision trees work, let's break down the process step by step. First, data collection. The first step is to gather a data set. This data set contains examples with features and their corresponding labels. For example, if you want to predict whether a customer will click on an ad, your data set might include features like age, location, browsing history, and whether they clicked on similar ads in the past. Next, feature selection. Not all features are equally important. The algorithm needs to identify the most relevant features for making accurate predictions. This process is called feature selection. Then, tree building. This is the core of the algorithm. The decision tree is built by recursively splitting the data into subsets based on the selected features. The goal is to create splits that separate the data into groups with similar labels. After that, stopping criteria. The tree building process continues until a stopping criterion is met. This could be a maximum depth for the tree, a minimum number of samples required to create a new split, or a threshold for the improvement in prediction accuracy. Finally, prediction. Once the tree is built, you can use it to make predictions on new data. The algorithm will traverse the tree based on the features of the new data point, ultimately reaching a leaf node that contains the predicted label. The first node in a decision tree is called the root node. It represents the entire data set. The algorithm selects the feature that best separates the data based on the target variable. This feature is used to split the data into two or more subsets. Each subset is then represented by a decision node. Each decision node represents a specific feature and a decision rule based on that feature. The process of splitting continues recursively for each child node until a stopping criterion is met. For example, imagine you want to predict whether a customer will buy a product based on their age and income. The root node might split the data based on age, with one branch for customers younger than 30, and another for customers 30 and older. Each of these branches would then become decision nodes, potentially splitting further based on income or other relevant features. Section 5. Branches and leaf nodes. The connections between nodes in a decision tree are called branches. Each branch represents a possible outcome or decision path based on the feature and decision rule of the parent node. The final nodes of a decision tree are called leaf nodes or terminal nodes. These nodes do not have any further splits and represent the final predictions or decisions. Each leaf node corresponds to a specific class label or a range of values for regression tasks. Returning to our previous example, the leaf nodes of the decision tree would represent the final predictions, whether a customer is likely to buy the product or not. For instance, a leaf node might represent customers younger than 30 with high income, who have a high probability of making a purchase. Decision trees have a wide range of applications in various fields due to their versatility and ease of interpretation. Here are some real-world examples. Medical diagnosis. Decision trees can assist doctors in diagnosing diseases based on patient symptoms, medical history, and test results. For example, a decision tree can help determine the probability of a patient having a specific type of cancer based on their age, family history, and biopsy results. Customer relationship management. Businesses use decision trees to segment customers based on their demographics, purchase history, and preferences. This information helps tailor marketing campaigns, personalize recommendations, and improve customer retention. Fraud detection. Decision trees can identify potentially fraudulent transactions by analyzing patterns in financial data. By learning from historical data on fraudulent activities, the algorithm can flag suspicious transactions based on factors like transaction amount, location, and time. Natural language processing. Decision trees are used in NLP tasks like sentiment analysis and language translation. For instance, a decision tree can analyze text data to determine the sentiment expressed in a customer review, classifying it as positive, negative, or neutral. These are just a few examples of how decision trees are used in real-world applications. Their ability to handle both categorical and numerical data, combined with their transparency and ease of interpretation, makes them a valuable tool in various domains. Decision trees offer several advantages that make them a popular choice for many machine learning tasks, easy to understand and interpret. Decision trees are highly interpretable even for non-technical users. Their tree-like structure visually represents the decision-making process, making it easy to understand how the algorithm arrives at its predictions. Handles both categorical and numerical data. Unlike some algorithms that require data transformation, decision trees can handle both categorical and numerical data without the need for extensive pre-processing. Requires minimal data. Pre-processing. Decision trees are relatively robust to outliers and missing values, requiring minimal data pre-processing compared to other algorithms. Non-parametric model. Decision trees are non-parametric models, meaning they do not make strong assumptions about the underlying data distribution. This makes them suitable for a wider range of data sets compared to parametric models. Despite their advantages, decision trees also have some disadvantages. Prone to overfitting. Decision trees are susceptible to overfitting, especially when the tree is deep and complex. Overfitting occurs when the model learns the training data too well, including noise and outliers, leading to poor generalization on unseen data. Unstable to data changes. Small variations in the data can significantly impact the structure of the decision tree, leading to different predictions. This instability can make the model less reliable in real-world applications where data is constantly changing. Can be biased. If one class or category dominates the dataset, the decision tree can become biased towards that class, leading to inaccurate predictions for minority classes. Not suitable for all tasks. While versatile, decision trees may not be the best choice for all machine learning tasks. For example, they may not perform as well as other algorithms for tasks involving complex relationships between features, such as image recognition or natural language understanding. Decision trees are a powerful and versatile machine learning algorithm used for both classification and regression tasks. They are easy to understand and interpret, handle both categorical and numerical data, and require minimal data pre-processing. However, they are also prone to overfitting, unstable to data changes, and can be biased towards dominant classes. Understanding the advantages and disadvantages of decision trees is crucial for selecting the appropriate algorithm for a specific task. By carefully considering the characteristics of the data and the goals of the analysis, data scientists can leverage the strengths of decision trees while mitigating their limitations.